A warm welcome to Electronic Circuits Lecture 7. In this video we will look at multi-stage amplifier, and we will come to know what is Cascade, Darlington and Cascode structures. So multi-stage, what is multi-stage? It is nothing but more than one stage. Why or what is the reason for more than one stage is, if the gain provided by a single stage is not enough, then go for multiple stages. So the first reason is gain improvement, and second reason is you can obtain desired input and output impedance. So for these two reasons you can go for multi-stage amplifiers, and you should be careful in the case of feedback amplifiers, because if you use multiple stages then feedback would become positive, and the amplifier purposes will not be solved when amplifier turns into positive feedback, because most of the amplifiers are negative feedback. When more number of stages have been included, the negative feedback amplifier may be converted into positive feedback due to feedback signal being in same phase, right? So this is the amplifier which contains Q1 and Q2, two transistors. So multiple stages have been present. Q1 is NPN and QP is PNP, and if you draw the small signal equivalent, you can obtain this step. So if you derive voltage gain, V0 is equal to this current which is been flowing. This is plus and this is minus. So GM2 V pi 2 is the current, and resistance is RC2 parallel RC1. If you want to know what is V pi 2, it is the voltage across R pi 2. So what is the voltage across R pi 2? This GM1 V pi 1 into RC1 parallel with R pi 2. So this is what is the V pi 2. So substitute this, and if you want to know what is V pi 1 here, V pi 1 is the voltage, here. So if you want V pi 1, then you apply voltage divider rule and obtain V pi 1. V pi 1 is equal to, the whole resistance is Ri, so Ri divided by Ri plus Rs into Vs. So substitute this, you will get to this form, which is GM2 into GM1, transconductance of the second transistor into transconductance of the first transistor, into RC2 parallel R2 parallel R pi 2, RC2 parallel R pi 1 into Ri divided by Ri plus Rs. This is the overall gain of the multi-stage amplifier, and this is called Cascade. This is called Cascade amplifier. Why? Because the amplifier, the first stage output is being fed to the second stage input. That's why it is called as a cascade amplifier, right? We will now understand what is Miller's theorem. If two terminals of a network are then interconnected by an impedance Z, and equivalent circuit can be formed. This equivalent circuit consists of same general linear network and two impedances, each of which shunt a network terminal to a common terminal. So suppose this is my input node, and this is my output node. So between input node and output node there is an impedance Z. So this Z, we do not know what is the impedance being offered by Z to the input side and output side. If that is the case, you can apply Miller's theorem and resolve into two impedances. One will be present at the input side and the other will be present at the output side. This is the meaning of the statement. Suppose for example there is an impedance reactance ZF. So this ZF is being present at the input side as well as output side. We do not know what is the effect of this reactance at the input side and the reactance at the output side due to CF. that is the case, apply Miller's theorem and resolve this capacitor CF into two equivalent capacitance or two reactants at the input side. So this is called input capacitance and this is called output capacitance. This has been obtained by applying Miller's theorem. So this, suppose if you consider Z in, this is what is Z in, which is equal to Z by 1 minus, so the output voltage is V2 and input voltage is V1. Similarly, if you want, so this is nothing but Z out, which is equal to Z by 1 minus Vx by Vy. Vx is nothing but the voltage at the first port and Vy is nothing but the second port. So this is what is the impedance which should be considered, or which should be this Z should be, or the CF should be resolved into two components, one at the input side and the others at the output side, and this formula will help you to calculate the values. And next is bootstrapping circuit, which is also called improving the input impedance. Suppose if you consider this common collector amplifier, the input impedance will be R1 parallel R2 parallel R pi plus 1 plus beta into R0 parallel RE. So this is my input impedance. So which is going to dominate the R1 parallel R2, which is going to be larger, and this quantity is going to be this quantity is going to be larger. This quantity is going to be larger because it is 1 plus beta R0 parallel RE. So this quantity is going to be larger compared to this. So the equivalent resistance is nothing but R1 parallel R2, because out of this combination R1 parallel R2 is the smaller, so the equivalent resistance or effective resistance at the input will be R1 parallel R2, which is going to decrease my input impedance of the amplifier. We do not want such configuration, so what we do is, but we need a common collector configuration at the output stages because current gain is beta. So if that is the case, you need this configuration at the output side. You cannot neglect common collector configuration. What you do is you modify at the input side, you put R3 and C2 and do the DC analysis. When you do DC analysis, capacitor should be considered as open circuit. So R1, R2, R3 is going to bias Q1. That's it. When you consider AC analysis, this capacitor is being considered as short circuit. So this R3 is going to be present between input and output, and the impedance offered by this capacitor is going to improve the input impedance of the amplifier. That's why it is called pulling up input impedance. Bootstrapping is nothing but pulling up the input impedance of the common collector amplifier, or you can take, for that case you can also take Darlington amplifier. So bootstrapping, literal meaning it's pulling up. Right, next is Darlington pair, where the first, it's also a multi-stage amplifier. The first stage is a common collector. So you are going to feed the input to the base and take the output from the emitter. Again you are going to feed the input to the base and take the output from the collector. So it is common emitter. So it could be common collector and common emitter, or it could be common collector and common collector. So input side, I am going to convert this Vs into a current source. So I have converted this into a current source, and I have drawn small signal equivalent, and Gm V pi 1 is the current source. This current source is equal to Gm V pi 1. So V pi 1 is II, which is this current into R pi 1. We know that Gm1 into R pi 1 is nothing but beta times II. So V pi 2 is the current which is coming through this path is II, and current coming from this path is beta 1 II. So the overall current is 1 plus beta 1 into II into R pi 2, which is the voltage across the second diffusion resistor R pi 2. So what is Gm R pi 2? It is nothing but beta 2 into 1 plus beta 1 into I1. So when I apply KCL at output collector node, I0 is equal to Gm V pi 1 plus Gm V pi 2. These two currents will add together, and at last when I find the current gain, I naught by Ii is beta 1 into beta 2. So what it conveys is, if beta 1 is suppose if it tend to be some 100, and beta 2 is tend to be some beta 1 you can consider it as 10, and beta 2 is considered to be 100. If calculate the current gain, it becomes 10 into 100, which is 1000. So that is the speciality of this configuration, where current gain is improved in the case of Darlington pair. That's why you are going for Darlington pair. And next multi-stage amplifier is called Cascode. The first stage, the input is being fed to the common emitter, because emitter is being grounded, and the second stage is the base is being grounded, so it is common base. So common emitter and common base is going to form what is called as cascode structure. If you draw the small signal equivalent, this will be the small signal equivalent, AC equivalent, and this will be your small signal equivalent. So if you consider this, the current flowing through the second transistor is IC2, which is nearly equal to IE2. This IE2 is going to flow into the collector of first transistor, which is IC1, and this is equal to IE2. So all are connected in series. So current GM1 and GM1 V pi 1 and current GM2 V pi 2 both will be equal. Why? Because they are connected in series. So output is nothing but V naught is equal to current into resistor. So current value is GM2 V pi 2. And why it is minus? So this current is been circulating here. So this tend to be plus and this tend to be minus. So it is minus. So what is V pi 2? The voltage across R pi 2. What is voltage across R pi 2? So when you want to find voltage across R pi 2, it is I into R. I is GM1 V pi 1 and R pi is R pi 2. If you take the output impedance of common collector or input impedance of common base amplifier, this is the input impedance of common base amplifier. So input impedance of common base amplifier is R pi divided by 1 plus beta, which is the impedance, and current is GM1 Vs. So that is what has been written here. You substitute for V pi 2, you will end up this. So GM2 R pi 2 is nothing but beta 2. So beta 2 divided by 1 plus beta 2. So beta 2, if you consider beta 2 as 100, 1 plus beta 2 is 101. So this is going to be nearly equal to 1. So it is V naught by Vs GM1 RC parallel R1. It is the gain of this structure is same as your CE amplifier. But what is the benefit of this configuration is nothing but Miller effect doesn't occur in common base circuit. Why? Because you are feeding the input to the first transistor, taking the output from the second transistor. If you take the second transistor, base is being grounded, so nothing is being fed to the input, nothing is being fed to the input. So there is no path from output to input. So there is no, you don't have any Miller effect. So this contributes the circuit to be applicable in high frequency circuits. So it is used for radio frequency applications, and this connection is been used for designing current sources to achieve higher. If you take any current source, the current source will have shunt resistance. This shunt resistance has to be much higher. Suppose if you want to design good current source, this R0 should be higher, and the cascode structure R0 is much higher. So it is suitable for designing current sources in integrated circuits. And that's all for this video. Thank you.